History of Malware, everyone. My name is Jan and I'll be your guide through the world of malicious software. In today's episode, we're going to take a look at where malware began, at the first documented malicious applications, and towards the end, even at source code of a recreation of one of the more famous types of malware out there. We will also correct a couple of common misconceptions related to the early malware. If you'd like to learn more about the subject we're going to be talking about today, you will find a link in the video description which will take you to a page with lots of historical documents. Now, without further ado, let's jump right in. Where did malware actually begin? Well, although it may sound strange, one of the fathers of modern computing is actually a spiritual father of some of the malware out there as well. I'm not talking about Charles Babbage, I'm talking about John von Neumann. Neumann was quite interested in biology, insofar as biological entities and their brains might be thought of as the most efficient computers out there, which was the reason why in September 1948 he participated in a Hickson symposium on cerebral mechanisms and behavior. Von Neumann presented his paper, The General and Logical Theory of Automata, on September the 20th. During this symposium, lots of specialists in different fields, mainly biology, presented their findings and papers. Neumann's paper was a bit different, as you may imagine. The talk was quite complex. He started discussing biology and moved on through neural networks to the idea of self-reproducing machines, which is the part we're interested in. During the talk, von Neumann discussed the capability of self-reproduction in terms of a Turing machine, i.e. Turing machine which would be able to read and write self-replicating code. Now, this was a good stepping stone for him, but von Neumann wanted to create a computer or a machine which would be able to create other and perhaps even more complex machines or automata. He explored this concept a bit further in his talks at the University of Illinois in 1949, which were titled The Theory and Organization of Complex Automata. From these lectures, a complex mathematical model emerged, which Neumann afterwards perfected a bit more. Von Neumann died in 1957, but his work on the subject of self-replicating machines was published in 1966 in a book called The Theory of Self-Reproducing Automata, which was edited by Arthur Burks. The book builds on the contents of the lectures which were originally given by Neumann, but contains a bit more detailed explanation. Some parts of the book were written by von Neumann while he was in the hospital before he died. In the book, von Neumann introduces a two-dimensional space inside of which machines, hypothetical machines, may move and interact with one another. Von Neumann built in this two-dimensional space a hypothetical machine called von Neumann's universal constructor, basically a machine capable of creating any other machine and copy of itself. What's interesting, besides the fact that von Neumann basically created a model for a self-replicating machine or a self-replicating code, as it were, is the fact that he also introduces the idea of mutations, i.e. changes from one generation of the machine to another. When a new machine is created, it might have some differences from the parent machine. Here we can see quite a nice analogy to the fact that code might mutate, which was later realized in practice in many types of malware. In his work, von Neumann didn't go too deep into the biological side of things. To him, the machines at their basic level were just black boxes which can deterministically turn input into output. But some other researchers went a bit further. One of these was Niels Al Baricelli, who in 1953, 54 and 56 conducted an experiment into artificial life at the cellular level. He modeled an artificial environment which simulated a living space, and inside of it, programs analogous to cells might join each other and create more complex cellular machines. He did his work on the IAS machine at Princeton. Given that this was one of the early computers, the world which Baricelli created was not too large, but still he managed to create a virtual environment inside of which symbiotic and parasitic relationships between different types of simulated machines or cells might exist. Although the evolution which Baricelli modeled inside the IAS machine didn't go too far, it always stalled after a couple of generations once a certain level of complexity was achieved, it's still a nice experiment. Although Baricelli's work was purely academic and his self-replicating cells weren't really a self-replicating code, it's nice to see how he built upon the ideas of von Neumann and what he managed to create. But Baricelli wasn't the only follower of von Neumann interested in self-reproducing machines. In fact, Lionel and Roger Penrose published in June of 1959 in the Scientific American an article titled exactly that, Self-Reproducing Machines. Now, Lionel Penrose, as the primary author of the article, went a bit different way than von Neumann did. While von Neumann's idea of a self-replicating machine was highly theoretical, Penrose went the mechanical way. Penrose describes the idea of a self-replicating machine using mechanical pieces which join together. Pieces of plywood or different levers which might join together and give each other information, i.e. the state in which different pieces of plywood are in. What's interesting for us, given our interest in computer viruses, is that Penrose actually mentions that the machines, self-replicating machines, which he devised are parasitic in nature and makes an analogy of these machines to viruses. He might be the first one to actually make this analogy of a self-replicating machine to a biological virus. Like von Neumann, Penrose also discusses the idea of changes during replication, i.e. mutations. But not only that, he also discusses the idea of self-changes, i.e. recombination of a machine without the need for it to reproduce. Many other researchers followed in John von Neumann's footsteps. Although work of these authors is interesting in its own way, it lies besides our main area of interest. We will instead take a look at where the Penrose's article led. In the fall of 1959, Frederick G. Stoll read the article by Penrose or by Penrose's. This man was already interested in the subject since he was aware of the work which John von Neumann did, and since he had access to an IBM 650 machine, he decided to try to make a digital universe which simulates some of these ideas. Originally, he wanted to make an extended version of John von Neumann's universal constructor, which might be able to move, and while he would simulate a couple of these machines, there might be a competition between them and he might see some sort of evolution. He realized immediately, however, that due to computational constraints, which IBM 650 had, he wouldn't be able to do anything as complex as that. This is quite lucky for us, since Stahl began at that point thinking of how he might make his hypothetical universe less computationally intensive. The idea he came up with was to actually make programs simulate the living entities. These programs would be able to replicate, they would be able to move through the memory of a computer, and therefore the entire memory space of the computer might be thought of as their living space. As you can probably imagine, making such a universe on IBM 650 still wouldn't make it too large. In fact, as Stahl himself wrote, it was only 1350 10-digit words long, although it was virtually connected, the end to the start, so in a circle, which made it theoretically infinite. An interesting idea which Stahl put into practice while modeling his universe was possibility for changes from one generation to another. So once again, we're talking about mutations. After he finished debugging the universe and the control program, which he called the Hand of God, Stahl decided in February of 1960 to launch its first run. Well, it turned out to be the last run as well, since it didn't go too well. As Stahl himself writes, the creature which originally inhabited the universe managed to give birth or replicate into another creature. This creature was able to move as well, so at least in this part it was a successful progeny. But afterwards, this second creature managed to eat the first one and another uncompleted progeny. This creature then infinitely moved throughout the universe and didn't replicate any further. As Stahl himself saw at that point, the first creature gave birth or replicated itself into a mutation which was unable to replicate itself further. This is actually one of the reasons why completely uncontrolled mutation was never an intentional part of pretty much any malware over the years. But we're getting ahead of ourselves. In August of 1961, there was another simulation which is worthy of our attention. While working at Bell Telephone Labs, Viktor Vysotsky devised a game which he called Darwin. Darwin was a game in which multiple programs were battling each other in a virtual memory environment, trying to destroy one another and trying to rewrite one another. The game was coded by Malcolm Douglas McIlroy on IBM 1790, and Vysotsky and McIlroy later played it with Robert Morris, who was their colleague at Bell Telephone Labs at the time. If the name Robert Morris sounds familiar and you're connecting it with the internet worm, to which we'll get in one of the future episodes, you're not far from the truth. The Robert Morris who played the Darwin game at Bell Telephone Labs with Vysotsky and McIlroy was father of the author of the internet worm. What's interesting is that according to Vysotsky, Robert Morris was the creator of the most lethal program devised in Darwin. So it seems that the ability to write aggressive code actually ran in the Morris family. It should also be mentioned that in a letter which Vysotsky and the other co-authors, as you may think of them, of Darwin wrote in 1971, they call the creation of McIlroy, which he made within Darwin, a virus. As we may see, the term, although it's usually being credited to people in the early or late 1980s, has a bit of a longer history. It's worth mentioning that some sources actually credit Dennis Ritchie as one of the authors of Darwin. Now, although Ritchie worked at Bell Telephone Labs at the same time and his accomplishments are many, next to the C language and co-authoring Unix, you might find many others, he didn't actually participate on creation of Darwin. Darwin became sort of a hit and was later recreated by many people. Probably the most interesting and important version was the game called Core War, which Alexander Dudney made with the help of one of his students at the University of Western Ontario, David Jones. Core War became quite popular in certain programming and hacking circles, and to this day you can find versions of it on the internet which you may download and play if you're feeling nostalgic. But let's move on to perhaps the first real malicious program. Some sources mention, although it's without citing any original source, so I mainly think of it as oral history more than anything concrete. In 1969, there was supposed to be the first fork bomb, or the first rabbit, as fork bombs are often called. It was supposedly launched at the University of Washington on the Burroughs 5500 computer. It's hard to say whether these sources can actually be trusted, as I've said, it's mainly oral history. But it's true that at the time there was a Burroughs 5500 used at the university, and it's a computer for which a fork bomb might actually be created. Now let's take a look at what fork bomb actually is. It's basically one of the simplest types of malicious software you might write. It's a program which splits infinitely, i.e. first run of the program creates 2 runs of the program, the 2 then create 4, and these numbers afterwards grow exponentially, as you may see. I've promised at the beginning that we will take a look at a modern equivalent of a source code for a well-known malware. Well, it's actually the rabbit or the fork bomb. Let's take a look at how we might be able to recreate this famous malware on modern Windows and modern Linux. Fork bombs, rabbits, or wabbits if you want, are usually quite simple, which means you may find examples of source code for them all around the internet. One source I would actually recommend if you would like to dig deeper into how fork bombs work is the malware wiki page, which you may see in front of you. It's filled with examples for different operating systems as well as for different programming languages. One which is actually quite nice and is intended for Linux, although it doesn't work as well as it used to, since some of the Linuxes out there are now hardened against it, is this one, which you may see right here. It's quite nice, quite elegant, although it may be improved upon a bit. But since you see that I'm running Windows here in the VM, we will try to actually crash it or make it as unusable as possible using just a simple fork bomb. Now I have here prepared a batch file on my desktop. Now if we try to type it, you may see that it's really simple. %0 pipe %0. Now what would happen if I were to run it? Well, let's try it and let's take a look at what happens using our friendly system view. And as you may see, the CPU usage as well as the memory usage actually spiked fairly well at the point where I ran the application. So even though it's really simple, it's basically just 5 characters, it may, as you may see, the Process Explorer just crashed. So as you may see, it can do real damage, even for modern Windows systems. So this is it. This was an example of how fork bomb might be recreated on a modern system. In 1970, the last simulation program which we will mention was published. It's quite an important one, not just because of its link or potential link to self-reproducing malware, but also because it gave us the so-called hacker logo. I'm talking, of course, about Conway's Game of Life, or just Life. Unlike Darwin or Core War, Game of Life is a simple 0-player simulation, i.e. you set up the starting conditions and then the game plays itself, if you want to think of it as a game. It simulates basic cellular life according to few simple rules. Of interest might be that since the game is Turing complete, one might use it to create the von Neumann's universal constructor, which is capable of reproducing itself. The second point of interest related to Game of Life we've already sort of mentioned. It's the source for the so-called hacker emblem. John Conway created the game of life in such a way that certain groups of cells might replicate in such a way that they actually move. Such groups of cells are called spaceships in Game of Life, and Glider is the smallest of them. For those of you interested in hacking history as opposed to just malware history, it's worth mentioning that John Conway actually expressed regrets for not renaming the glider as an ant. So we might have had a hacker emblem which would be called ant, not that it would matter that much. If you're interested, I recommend you wholeheartedly taking a look at an interview with John Horton Conway in which he discusses Game of Life. I'll put a link in a description. Although it will date the video a bit, I feel it's only right to mention that John Conway actually passed away from complications related to a COVID-19 infection about a month before this video was published. His work lives on, however. If you'd like to try Game of Life, there are many chances both online and offline. And if you're interested in mathematics, Conway's work was actually quite a bit wider than just his experiment with Game of Life. But let's get back to 1970. In the same year when John Conway published his Game of Life, Gregory Benford wrote an interesting piece of short science fiction. It was a story called The Scarred Man, and it was published in the May issue of Venture magazine. Why is it important for us? Well, it's the first work of fiction where the word virus is used for a malicious computer program. Let's leave aside that the description which Benford used for the virus would actually be more suitable for a worm. It was still an interesting piece of fiction, although, as we mentioned before, there have been analogies drawn between computer programs or machines which replicate and viruses before that. The Scarred Man is actually the first instance of anyone calling a malicious program a virus. So this would appear to be the original source of the term. If you'd like to take a look at The Scarred Man, its author has actually published it freely on his website for anyone to read, so you may do so. I will put a link for it in the description. As you may see, by the end of 1970, we've had pretty much all that was necessary for someone to write a self-replicating program. It actually didn't take too long. In 1971, the first program, which might theoretically be called a malware, although the term wasn't coined at that time, was published. It was called Creeper, and although many sources claim it was the first virus, it wasn't, it's more of a worm, but let's leave that to the side. It wasn't malicious in any way. In 1971, the internet didn't exist yet, but there were a couple of large-scale networks. The most important one among these was the ARPANET, and one of the companies which helped develop it further was Bolt, Beranek and Neumann, or BBM Technologies. This company, amongst its other accomplishments, created a well-known operating system for the PDP-10 computer, which was called 10X. One of the developers behind the 10X operating system was Robert Thomas. Now, Thomas, besides working on 10X, also worked on so-called Resource Sharing Executive, or RSExec. RSExec was a mechanism which was supposed to allow applications to jump from one computer to another in cases when the target computer would be better for running the application, i.e. it would either have the data or it would have unutilized computing resources. Bob Thomas wrote Creeper as a demonstration program for RSExec. It was a program which jumped from one computer with 10X to another, and on each PDP-10 it visited, it printed out under Creeper Catch Me If You Can, probably so there would be some record that Creeper actually visited that computer. Now, since it was using the rsexec API in order to jump to the target computer, and all the operators of all the computers to which Creeper jumped were actually part of the experiment, we can't call it a malware. It did exactly what it was supposed to do. It didn't crash any services, it didn't cause any problems. Now, since Creeper spread from one computer to another and then spread further, it's actually the first instance of a computer worm on record. But not just that, it's an instance of a very special type of worm or special type of malware, which is unfortunately sometimes also called rabbit. So we have rabbit malware, i.e. the fork bombs, which we've already mentioned, and we have rabbit type of worm. Now, the rabbit subtype of worm is specific by jumping from one computer to another, disinfecting the last. So as you may see, in this case, it's completely applicable. The story doesn't end there, however. Raymond Samuel Tomlinson, the man who's probably best known for basically inventing modern email, worked at BBN at the same time as Bob Thomas did, and he modified Creeper in such a way that it didn't only jump from computer to computer, but it was able to replicate, i.e. when it jumped, it didn't always disinfect the last host it visited. So, as we may see, Bob Thomas probably created the first, I don't want to say malware, but the first worm, specifically rabbit type of worm, and Tomlinson afterwards changed it so it behaved more like a regular worm. But even this modified variant didn't mean to do anything malicious, it was just a proof of concept for basically distributed computation. As we've already mentioned, all the operators of all the machines which Creeper visited actually participated in the experiment, and to tell you the truth, there weren't that many of them. There were at that time only about 28 computers which Creeper might visit. Still, since the self-replicating Creeper from Tomlinson might perhaps stay in the network while it was not beneficial or intentional for it to be there, Tomlinson created what is sometimes called the first antivirus. It was a program called Reaper. It used a similar technique of spreading, if you will. It visited all the machines which theoretically could host Creeper, and if it found the Creeper process there, it stopped it. So once again, whether to call it the first antivirus, since Creeper in either of its iterations wasn't really malicious, is something I will leave up to you, but it was definitely what's called a first nematode. Nematodes are a special type of malware, usually worms, which destroys other malware. In this case, although none of these were actually malware, the term definitely applies. In 1972, about a year after Thomas's and Tomlinson's experiences with Creeper and Reaper, Veit Rezac publishes an article titled Self-Reproducing Automata with Minimal Transfer of Information. It's interesting for us because although it's an academic work, it's not purely theoretical. In fact, alongside the article, Rezac published the source code for his self-replicating program. The application was called ReapOut, and it was a program written in the assembly language of Siemens 4004/35. The program was only 1200 bytes long, although it was written in assembly, so there was not much of a reason for it to be larger, and it could replicate inside the memory of a target Siemens system at most 16 times. Since Rezac didn't want the program to do anything malicious, it stopped replicating after it filled the available memory. Reza's program was sort of an evolution of the original John von Neumann's idea, and although it's hardly a computer virus, we're slowly getting to the point where a computer virus might actually be created based on this theoretical work. While on the topic of viruses and 1972, we should mention that David Gerald published a book during that year titled When Harley Was One. It was a sci-fi novella, and in it the author uses once again the term virus to describe a malicious program. As we've already mentioned, it's not the original source for the term virus to describe a malicious piece of code, but it was one of the first ones. Also of note is that the virus, well, it's a worm actually, which is described by Gerald in the book, actually jumps from computer to computer, disinfecting the last one, basically, but it later mutates and starts spreading uncontrollably. We may see that although Gerald didn't coin the term virus, he was probably the first one to actually describe a rabbit worm. Since we've mentioned rabbits, in 1972 we have first documented instance of a rabbit being created, at least going by the interview with its supposed author. The author was Q the Misanthrope, a person who later became one of the early virus authors, and in an interview he mentions that in 1972 he wrote his first fork bomb or rabbit in BASIC. What's interesting is that at that time he was only in 7th grade. In 1974 there was supposedly a new rabbit, or wabbit if you like, created on the IBM 360. It's again an oral history tale, although in this instance we at least know the original source of the information. It was Robert Kennedy on a RISC Digest emailing list. Basically it was an emailing list. And he mentions that in 1974 he knew of a what he calls a bright young fellow who worked for a company with 3 IBM 360s and created a fork bomb, which afterwards crashed all the computers. He ends the story with saying that the bright young fellow was let go because of this incident. Whether it's true or not, it's hard to say, but the mention definitely exists. Now, whether the 3 fork bombs, rabbits or wabbits, we've mentioned actually existed or not, it's almost certain that the fork bomb concept has been with us for some time in 1974. So it's certain that there have been multiple instances of fork bombs. However, mentions of them in any relevant historical sources are few and far between and are mostly really general. So there most certainly were more, but we have to be satisfied with the 3 examples which we've already mentioned. In 1974, John Walker, one of the founders of Autodesk and creators of AutoCAD software, created an interesting game called The Animal. It was a version of the 20-question game where the computer asks you questions to which you reply yes or no, and the computer guesses which animal you're thinking of. Now, as Walker himself tells the story, the game became quite popular in the programming circles of that time because it was quite sophisticated, and he was asked again and again for copies of this game, which supposedly led him in January of 1975 to create a program called Pervade. Together, Animal and Pervade, although in some sources they're considered to be one single program called either Animal or Pervading Animal, might be thought of as the first Trojan horse. What Pervade did was to actually create a self-replicating mechanism for any other program to which it was attached. When it was attached to Animal, it worked in the following way. Each time the Animal program was run, The pervade part would take the program and replicate it, copy it, into any folder for which the user running the program had access rights. So Animal started spreading quite fast on a single system. Animal was written for UNIVAC 1100/42, and these computers weren't really often connected in such a way that they allowed a remote network access to folders. So Animal didn't spread over a network. However, if an administrator or privileged user, as the role was called, ran Animal, since he had access to all the folders on the computer, Animal would spread into all the folders on the computer. And since it was a common practice to transfer data from one computer to another on tapes using just copies of specific folders, it might fairly easily transfer from one computer to another. Now, Walker himself mentions that Animal spread fairly wide in the wild due to this, and there's no reason not to trust him. Now, although it's hard to call this Trojan horse a malware since it didn't do anything too bad, it just spread in a way in which no one wanted it to, no one besides the original author, that is. It's true that it managed to at least take up some space on the drives of the specific computers it infected. However, Pervade was quite well written, so it didn't tax the computers too much. It didn't replicate the Animal inside the same folder multiple times, only once. And if a new version of Animal and a new version of Pervade were to infect a computer, they would just rewrite the old versions. Still, it probably wasn't that great that Animal started spreading, which is the reason why certain colleagues of Walker's actually presented a proposal for making a so-called hunter program, which would be able to kill the Animal. Now, although the story of the hunter program actually being created may be found in certain sources, going by Walker's own testimony, it never was. What stopped Animal from spreading in the end, however, was a normal update to the UNIVAC's 1100/42's operating system, the exec8. The update in question changed the way in which the operating system or programs interacted with the file system. Due to the changes which this update made, anytime an Animal was run, Pervade would actually check all available folders and it wouldn't find any which would be a candidate for writing Animal in it, so it wouldn't spread any further. All one had to do was update the operating system. It's actually sort of reminiscent of our current predicaments with modern malware. In 1975, another John Brunner, created an interesting and important piece of sci-fi. It was called The Shockwave Rider. Now, this book is important because John Brunner was the person who coined the term worm in it for a program which is capable of transferring itself and spreading itself over a computer network. Brunner actually calls these programs tapeworms, but he does use the short version of worm as well. Now, besides being interesting for this reason, the book actually provides quite a good read as well. So if you are interested in the history of malware, and since you're looking at this video, I assume you are, if you didn't have a chance to read The Shockwave Rider, I recommend you do so. It's sort of a mix between Matrix and V for Vendetta. Among readers of Brunner's Shockwave Rider were also two researchers, or at least two researchers, at Xerox's Palo Alto Research Center, or PARC. Xerox PARC is well known for being the birthplace of one of the first personal computers, of GUIs as we know them today, and the Ethernet, but it's less known for being the birthplace of the first computer worms, or rather the birthplace of the first programs which were called worms. And it was because of John Brunner's book. The two researchers at Xerox PARC who read the shockwave writer were John Such and John Hupp. These two were working on a project for distributed computation, basically a way in which they would be able to take any program and make a distributed program out of it. So in this way, their work was quite similar to the one done by Tomlinson and Thomas at BBN with Creeper. Such and Hupp created their worm program, as they called it, in 1978, or probably in 1978. Most sources say 1979, but going by the history, which used to be on Xerox PARC's official webpage, it should be 1978. Their worm programs were mainly experiments. They created, besides worms that just spread and did nothing, worms which acted as a sophisticated distributed alarm clock, a worm which was capable of computing an animation on more than one computer, and a worm which was serving as a diagnostic tool for the Ethernet network over which it spread. From a technical standpoint, it was actually quite interesting. Basically, the two researchers saw a distributed computation as a single computer computation or single CPU computation where the CPU had many cores. They tested at the Xerox PARC own network, which at that time comprised of more than 100 Alto personal computers and several servers which are not of importance for us. Now, the worm program spread through unutilized Alto computers. A special mechanism was used to determine whether a computer was unutilized, and if it was, the worm, which was supposed to be computing something, spread to it if it was supposed to look for another target. All the worms had specific lengths which they should be, and if a computer started being used for some different purpose, the worm would find a new idle computer to which it would spread. In theory, great. All the worms were so-called multi-segmented, i.e. the part which was on each computer was called a segment, and the segments as a whole created one worm. The researchers published their findings in 1980 and then again in 1982 in Communications of the ACM under the title The Worm Program's Early Experience with a Distributed Computation. And from this article it's clear that they really were fans of Bruner's book, since they actually quote it in more than one instance. The article which they published describes in a nice level of detail how the worm actually spread. It used rebooting of the machines in order to, I don't want to say infect them, but basically yes. When an idle computer was found on the network, if a worm wanted to spread to it, it asked it to reboot. Now, if a computer was running any software, any program at that time, it wouldn't do so. But if it was idle, it rebooted. And since it was instructed by the worm to boot from a network location, i.e. the place where the worm itself resided, it would be loaded into the memory of the computer. So quite a simple and effective solution. Where it became problematic, however, were the night runs and even a couple of day runs. As you may see, these worm programs weren't intended to be malicious in any way. No one wanted them to crash computers or do anything other which might be called malicious. Unfortunately, it doesn't always work out the way one might expect or one might wish, and that was the case of PARC's worms. The authors in the article actually mention a couple of instances when the worm did crash machines unintentionally. In at least one instance, it was supposed to basically repeatedly crash all 100 computers which were connected to the Xerox PARC network. However, since they were very cautious from the beginning, they put a mechanism into the worm which, after receiving a specific packet over the network, would stop all worm processes on a specific computer. So if they wanted to disinfect all the 100 computers, they only had to send this specific packet to all of them and the worm would stop. Although this was a nice way to stop the worm from wreaking havoc over the Xerox PARC network, the fact that it did infect unintentional hosts actually foreshadowed the future development of worms as destructive tools. But that's a topic for another day. If you've enjoyed the first episode of History of Malware, please subscribe, like the video, and if you have any questions or comments, don't hesitate to contact me.